Hi everyone, and welcome to the final iteration of the COMSOC seminar before we break for the summer, and after which we will return in September with a new slate of speakers. But today we have two exciting speakers with us. We have Sanjukta Roy, who is going to tell us about quantile agent utility and implications to randomized social choice. And then later, after we have our nice kind of breakout session, then Rupert will take over and tell us about reallocating wasted votes. So let's, Sanjukta, you can take it away.
Share my screen. Is it visible? Okay.
It is.
Okay. So let's get started. As Nishad mentioned, that I will talk about something called quantile agent utility. So this is a joint work with Yanis Karagianis, and I am Sanjukta. I am an assistant professor at Indian Statistical Institute. Okay, so we will, it's a very ambitious goal for a 20-minute talk, but we are planning to look at three different setups: voting, one-sided matching, and two-sided matching. And we will look at this thing called quantized utility. But before I go into this, just to motivate that we have a very rich theory of deterministic voting rules and deterministic matching mechanisms. For example, there are celebrated theorems like Giver-Satterthwaite theorem, or top trading mechanisms, or deferred accepted mechanisms for matching markets. What about randomized rules and mechanisms? So when the agents in a deterministic setup, if the agents have strict ranking over the possibly available options, they know how to compare two outcomes just based on their ranking. It is well defined. How do I compare, or how do an agent compare things in randomized setup? So in the randomized setup, the agents are the outcomes are lotteries. So the agents have to compare lotteries over some options or the alternatives. So one possible answer could be to have each of the agents have cardinal values for the options, and we compute expected utility, and they compare based on this expected utility. But what if I do not have cardinal values for each of the options? The agent's cardinal values are not known. Then we need to define some lottery extensions, like based on stochastic dominance. So there is an excellent survey by Felix Brandt called Rolling the Dice on it. So this is another method that we are proposing for comparing lotteries by the agents, so which we call the quantile agent utility. So agent I has a strict ranking of the available options, which is denoted by successor I, and they also have a quantile parameter hi, which is between 0 and 1. And to evaluate a lottery it is done as if it would be done in a deterministic setup. So for each lottery, the agent identifies something called a representative option. And if this representative option is better, so they chooses that lottery which gives them the best representative option. What do I mean? So formally, the definition is as follows. If the quantile parameter hi is 1, then the representative for a lottery X is for the agent I with quantile parameter hi is the best option A under this preference of I, such that A has a positive support, A has a positive probability. And if hi is something between 0 and 1, but excluding 1, then the representative is the worst option A, such that A has positive probability, and everything, if I sum over the probability masses of the options that are worse than A, this is at most hi. Okay, so So if the agent has HI equals to 0, then this would be the worst option with positive probability, right? So let's look into an example to understand the definition. So let's say I have these 5 options, A, B, C, D, E, and the agent preference is this: A is better than C, better than D, better than E, and better than B. And we are given this lottery X with this probability distribution. Now let's say if the quantile parameter is 0, so then what we said is that the representative is the worst option with positive probability. So then B would be the representative of for this agent. But if the quantile parameter is 1, this is the best option with positive probability. So this is the first option, has the top choice has positive probability. So this would be A would be the representative. For any other quantile parameter, let's look at something like a median value, so half. Then the quantile, the representative is the option, the worst option, whose value is positive. And if I sum over the probability masses over the options that are worse than this one, the value E here, has to be upper bounded by the quantile parameter. So if I look at B here, the probability at B is 1/3, less than equals to half. But when I sum these two values, it is at least half, more than half. So that means E is the representative for this particular lottery if my quantile parameter is half. So is the definition clear so far? Okay, so I will move on. So, okay, so one of the lottery extensions that is very widely used is stochastic dominance. So we say that a lottery X over a set of alternatives or set of options A is not stochastically dominated by another lottery Y if the following holds: that for every option O, everything that is less preferred, or at least as good as O, the sum of probability values that those options is upper bounded by the sum of probabilities assigned to those options in Y. And stochastical, so the one problem with stochastic dominance is that we cannot compare all lotteries. For example, here I have two lotteries X and Y, and these two lotteries are incomparable. We can check that if I look at the alternatives that are at the bottom half of this preference, X looks better, and at the top half of the preference, Y looks better. So there are all lotteries that are incomparable with respect to stochastic dominance. So the features of quantile agent utility is that firstly, for every lottery we are defining a particular option as representative. So the comparison for the agents are very akin to deterministic outcomes, and it may happen that different agents have different representatives. It may also happen that two different agents have the same representative. But we don't need cardinal utilities. The whole setup can be defined for ordinal preferences, unlike expected utilities. But unlike stochastic dominance, we can always compare two lotteries because we will always have the representative for these lotteries, and we can compare this representative. If I compare this with stochastic dominance a little bit more, so stochastic dominance is more stringent in the sense that a lottery X is not stochastically dominated by Y if and only if X, the representative of X is better, sorry, X is stochastically dominated by Y if and only if the representative of X is better than representative of Y for all possible quantile values. So for every quantile value, if X is better than Y, then only X will stochastically dominate Y. So I have a much more larger set of things to a set of lotteries when I'm looking at, let's say, an efficient. So I will define efficiency, and these things will make more sense then. Okay, so let us first go into the first domain that I mentioned of social choice is voting. And so in voting, we are familiar that we have M alternatives and we have N agents. And now each agent has a quantile parameter given by H1 to Hn. And the agents has preference ranking. So a voting rule now takes this profile, the quantile parameters, and returns a lottery over the alternatives A. So this lottery is efficient if there is no other lottery Y such that Y gives a better representative for some agent I star, a strictly better representative for some agent I star, and for every other agent, the representative is at least as good. Okay, standard definition of efficiency. But here we are only looking at the representative to compare. So some observations about quantile comparisons of lotteries. So if the quantile values are small, then for example, if the quantile parameter is 0, the only efficient lottery over alternatives are deterministic. If we have large quantile values, so it's like 1 minus 1 by m, where m was the number of alternatives, uniform lottery makes top alternative representative for every agent, every voter. And a lottery of over alternative is efficient for a given profile, and every quantile vector if and only if all agents agree on their top alternative, which is very restricted setup. So generally, obviously, agents do not agree on their top alternative. Then we need, so this result kind of says that it doesn't make sense to look at which characteristics or which properties hold for all quantile values, but we can fix quantile values for the agents, a quantile vector for the agents, and look at results for that for a particular quantile vector. So so before I go into the particular quantile vectors and what results we are getting there, we define strategyproofness as so given a domain which is the set of alternatives and set of agents and the quantile vector, if for every profile successor and every agent I, it holds that I cannot lie and get a better representative, then we will say that this is strategy proof, right? So now one of our reasons to define strategy proofness is to see that can we does the Gilbert-Stackleworth kind of impossibility result still holds when we have such quantile representations? What we show is that if I have just two alternatives, then we can have a rule which is strategy proof and efficient. And this rule is defined as follows. So it's looks like a little bit of case analysis, but it's basically based on plurality. So we are saying that we have two alternatives, A and B, and A is the plurality winner. Then I want to give all the agents who likes A better than B, we want to have that these agents has A as their representative. So to do so, what I have to do is the voting rules should assign probability 1 minus HI. So if agent I have A as a representative, the probability assigned to A should be at least 1 minus HI. So this is why we look at the minimum value of HI that any agent has, the agents which like A better than B, and for this minimum value is assigned to be the probability mass for B, and then the remaining is assigned to A. Then every agent who likes A better than B has A as their representative. In the other case, if this value is set to this value is not less than 1, the minimum is not less than 1, that means every agent who likes A better than B has quantile parameter 1. So quantile parameter 1 basically means that the agents are very optimistic, and 0 means they're quite pessimistic, because 1 basically means that if you give a very small probability to their top alternative, they will consider that as their representative. So if we are not in the first case, the quantile parameter is 1 for every agent, then I want to max, because we are looking for an efficient solution, then we want to maximize the agents with B top, who has B their top choice, should have B as their representative. So this is what is being done in the next two cases. Basically, in the interest of time, I will not explain it more, but this is just a very simple rule based on the plurality winner, but this only happens when we have two alternatives. When we move to three alternatives, what we have is when the quantile parameter is small, between 0 and 1/3, then the only rule that is strategy proof and efficient is dictatorship. If it is between 1/3 and half, then the voting rule for two agents is dictatorship. So two agents, three alternatives, the only rule you can have is dictatorship. And for larger values of age, if age is at least half, then there exist non-dictatorial rules. And this is very simple. Like one non-dictatorial rule would be to select among the two alternatives that has highest plurality scores, equiprobability. So we assign half to each of them, the two alternatives with highest plurality score. And if the quantile values are between 2/3 and 1, just take an uniform lottery. So when the agent quantile values are high, it is easier to construct, or we are more farther from the deterministic setup than the classical. It is easier to construct voting rules which avoids the classical impossibility results. Okay. So the open question is that, so we have, with the three alternatives, we already see that we need to look at these different cases, or two, at least four cases here where different things are happening for the different quantile values. So what would be a characterization when we have at least three alternatives and different quantile vectors for strategy proofness plus efficiency? Okay, this is in voting. I think I have like 5 minutes left probably. So I will probably have no time to go into the two-sided case, but I will quickly define the one-sided matching setup. So it is the standard, we have n agents and n items. So I'm assuming we have equal number of agents and items, and every agent has a quantile parameter hi, which is, and they have a ranking over the items of M. Now we are looking for lotteries over matchings. Unlike voting, where we were looking for lotteries over the alternatives, now we are in the matching setups, we are looking at lotteries over the matchings. So that basically means that, yeah, a lottery X looks like XIG, I belongs to N and G belongs to M, such that this XIG values are at least 0, so positive, and the sum of XIG for each I is 1, and the sum of XIG for each G is also 1. So it's a doubly stochastic matrix basically. And so this is an example of two-sided case would be this is a matching of agents to items. So what we have that the agents have preferences and they also have quantile parameters. So here it means that agent 1 has quantile parameter 1/3 and this is his preference. Now, this could be a lottery, which assigns probability 1/3 to this matching, half to this one, and 1/6 to this one. You can check that the green highlighted option, the items are the representative for these agents. Okay, so what we want to look here, well, first thing we check is we study is can we give the agents a good lottery? So can we maximize the agents who will have top choice as their representative? And this can be done in polynomial time. I will skip this part. But if we want to do something like rank maximization, so for each agent, I have a fixed rank Ri, and I want to know that can this agent have some representative whose rank is at least as good as Ri? Can we do that in polynomial time? Can we have the sum of ranks minimized? These questions are open. And then we can, so I will actually skip this. We also define proportionality. So uniform lottery will be proportional. So I will not go into the definition, but we define proportionality, and we also, so what we show is that an efficient proportional mechanisms can be found by something like probabilistic serial dictatorship, but this will not be strategy proof, first, very strangely, because of the proportionality rule. So we start with the proportional matching, and then we keep on improving to ensure efficiency. And the small example shows that it will violate strategy proofness. So the question here is that can we find efficient strategy proof and proportional mechanism? And then we define envy freeness. So the envy freeness would mean that in the lottery, my representative should be at least as good as anybody else's representative with respect to my ranking. And as we have in the classical setup here, we also have that envy freeness implies proportionality. We know that efficient and envy-free lottery may not exist. What we do not know is that what is the complexity of deciding whether an efficient and envy-free lottery exists in one-sided instance. I will skip the two-sided instance. We look at stable lotteries and efficient, stable, and strategy-proof lotteries here. And this is my last slide. So we so we looked at this voting one-sided and two-sided and some questions in this setups. There we also looked at efficiency and strategy proofness, social welfare, stability. There are other setups in computation social choice like fair division, and in all of these we have randomized mechanisms very well studied. But what happens if we are looking at quantile, if we consider quantile utilities for the agents? And so this is basically the start of all these questions, I would say. Okay, with that, I will end my talk. Thank you, everyone.
Right, let's thank the speaker. So if you have any questions, feel free to raise your hand and just directly ask your question. Oh, Peter, go ahead.
Yes, thank you. For clarification, I have the impression that you assign the quantity level, which is an essential ingredient, to the agent, and that you keep it fixed.
Yeah.
So that immediately suggests that there should be a way of further strategizing by the agents by misrepresenting their quantity level.
Yes.
Have you considered that?
Yes. Yes. So initially, when we started to look at strategy proofness, we were actually letting the agent change everything, but that gets very messy, I would say. So I think the first setup would be to keep the quantile values fixed and see what kind of impossibility results we can ward off. But if you let the agents misreport their quantile values, we don't have any results yet. But yeah, it would, I think, allow for more impossibility results than anything else.
Thank you.
A good question. Yeah, that definitely makes sense.
Right. I have a question. So I was thinking of like how this kind of idea, whether we can use it to lift up the preferences over individual alternatives to other kinds of comparisons. And I was thinking of committees over alternatives. And there kind of the natural version would be that every agent I has a parameter hi. So if we are looking at committees of size k, then they have a parameter hi that's somewhere between 1 and k. And then they look at kind of the hith alternative in the order of their preference as their representative. So you have committee of k alternative, and if my number is 5, then I look at basically like the fifth alternative from the bottom inside that committee in the order of my preference as my representative. And this actually, yeah, go ahead.
Oh, continue.
No, I was just saying that, do you know if like this has been broadly studied, this kind of extension?
Not really. So what you were saying is basically instead of doing this extension for randomized outcome, to do it for set extensions,
Right.
right?
Yes.
And I know that there is a recent paper on arXiv from this group from UNSW, Harris Aziz, and some others who are looking at set extensions based on quantile values. I forgot how their paper is called, but their paper title also have the word quantile in it. And it came out very recently as well. So, but I think they are only looking at maximizing social welfare and so utilitarian and egalitarian, I think. But the setup is like fair division, so they are assigning bundles, but it definitely makes sense for committees as well. So yeah,
Right.
lots of open questions.
Yeah. If nobody answers the question, I have a follow-up question regarding your slide. So for fair division, I guess like were you thinking of extension to bundles or distribution over, I mean, allocations?
We were thinking of what we were saying. We were thinking of was distribution over allocations, extensions to
Starting with
bundles.
ordinal preferences over bundles of items, or just ordinal preferences over individual items?
Yes, we haven't actually defined it,
Okay.
so we can, yeah, it could be either. So that's open. Yes, we haven't done anything for the fair division part yet.
Yeah, that's what got me kind of thinking about because there, like, you already know how to handle the distribution, but now we also need to compare bundles, and if we only have preferences over individual items, then we don't know how to compare bundles. And I was thinking, oh, I don't know the answer there, but at least in kind of voting in committee selection, when the committee size is fixed, then at least or in many to many matchings, or in many to one matchings, there at least you can also have this additional parameter. So you find the hith representative in terms of the lottery, that gives you a set, and then you find kind of some lith item in the set, and then you compare those.
I think another way could be to think of it as like fractional bundles, and
Directly
then
line it up
compare.
on the. Yeah,
Yeah.
that sounds good too. Any other questions?
So I see there is something in the chat, but I'm not able to open it.
No, so Rob just said that Peter beat him to the question.
Oh, I see. Okay.
All right. If there are no other questions, then let's thank the speaker again.
Thank you.
Right.
Stop sharing.
And now we are going to do our usual breakout session for about 10-ish minutes, I believe. Yeah, I get a nod from Dominic. So let me. All right, welcome back, everyone. Now we are ready for our second talk by Rupert Freeman, who will tell us about reallocating wasted votes in proportional parliamentary elections with thresholds.
All right. Thank you, Nisa. You can see and hear this?
Yes, we can.
All right. Thanks. I'll be talking about joint work with Théo Delamazure, Jerome Lang, Jean-François Lallier, and Dominic Peters. We have, if you include our experimental participants, we have a little over 4,000 people involved in this project, and you're hearing from the only one who is not French. Well, Dominic, I guess, counts as French these days, to me at least. Okay, so let's get going. We're going to be interested here in electing a parliament. So here are some pictures of parliaments. When I say electing a parliament, I think about allocating some number of seats between political parties in a way that represents voters. So hopefully people are kind of convinced that this is an important and interesting problem to study. Oh, here we go. Okay, one kind of natural, perhaps the most naive, simplistic way you might want to do this is, especially if you're shooting for some kind of proportional representation, is to have voters vote for a single party and then allocate seats in proportion to the scores or the number of votes that each party receives. So you'd get a picture that looks like this, translating votes to a parliament. However, what this can end up with, although it's good for proportionality, you can end up with a somewhat fragmented parliament where you get many parties, some of which are very small, and this can make governing difficult in terms of coalition formation to form a government. So many parties address this by imposing a threshold to reduce this fragmentation. So a common number is, say, 5%. And they simply say that any party that receives less than 5% of the vote won't be represented, and the seats are allocated proportionally among those parties that get 5% or more of the vote. Okay, so we get this parliament, which seems to be a little less representative, but perhaps more stable. The parties are larger, there are less of them. Okay, so this comes with some costs. In particular, the one that we'll kind of think about most in this work is that some votes are lost, in the sense that supporters of D and E have no influence on the seat distribution. As a kind of direct result of this, these systems incentivize forms of tactical voting or strategic voting. This can take several forms, but the most straightforward one is that voters who might support small parties are nervous about voting for them because their vote might be lost. So if you like D or E here, maybe there's an argument to be made that you should vote for A, B, or your preferred party of A, B, or C, so that you have some impact on the outcome. And this sort of narrative is very, very prominent in the discourse in countries that implement these schemes. Additionally, it hinders the growth and development of small parties because this threshold can be burdensome. So creating a new party, it's kind of likely that you never meet this threshold. Okay, so here are just some examples of the sorts of numbers that we might be seeing. So in 2019, election of French representatives to the EU Parliament, threshold was 5%, but around, well, exactly 20% of votes were actually lost, in the sense that they were cast for parties that did not reach the threshold. A particularly extreme example from Turkey in 2002 had almost half of the votes go to parties that did not reach the threshold. So this certainly has real impacts in terms of proportionality in these elections. So our idea here is going to be to allow voters to rank parties. This is often known as a replacement vote or spare vote in the electoral reform discourse. Of course, this is not a new proposal. Everyone here is very familiar with allowing voters to rank parties. However, we're not aware of a social choice theoretic treatment of this particular topic. So that's kind of the goal of this work, is to study some rules in this space formally. Okay, so let me start by giving you the model that we're working with. We'll have voters submit truncated rankings over parties. And then we'll have a party selection rule that takes as input a preference profile, the set of rankings, and a threshold. Thresholds for us will be numbers of voters rather than a fraction of voters. That just makes our notation a bit easier. And outputs a set of parties, S, that we do allow to be empty. There's going to be some conditions on this set, though. So we'll say that voters are represented by their most preferred party in S. And then we'll say that an outcome is feasible if every party represents at least tau voters. Okay, so another way to say that is that every party in the parliament must be the most preferred party among those in parliament of at least tau voters. That's our way of encoding the threshold. So we're going to insist that our party selection rules always output feasible sets of parties. We'll think about these rules as outputting sets, but then the idea is that they get translated to a parliament in the sense that selected parties get a number of seats proportional to the number of voters that they represent. Okay. Just interesting to note that when tau equals n, so our threshold is all voters, and we have full profiles in the sense that every voter casts a full ranking, a complete ranking over parties, then we actually recover single winner voting as a special case, because when the threshold is all the voters, you can't select sets of size greater than 1, because there's simply, no party could reach the threshold if you select 2 parties. They need the support of all voters. So we get single winner voting back, and that will have some consequences as we move forward. Okay, so let me introduce the three rules that we're going to consider, and then I'll tell you.
Excuse me, Rupert.
Yes.
So, isn't it true also that for lower thresholds, which are greater than majority, this is also single winner voting?
Yes. So right.
Okay.
Good. Thank you. So I wrote here tau equals n. Any threshold greater than n over 2 will give the same result. Good. Okay. So first, the first rule that we consider is probably the most similar to the rule that we see implemented in practice. We call it direct winners only, and this works by selecting the parties that receive at least tau first place votes. So here's a little example that I'll use to introduce the rules. So we have 5 types of voters, 4 parties, A, B, C, D. So the ballots are on the left. We have a threshold of 5. We see that here party D is the only one with plurality vote that exceeds the threshold. So the outcome here would simply be to select party D. They would get all the seats in parliament. The first 3 types of voters don't actually rank D on the ballot. So here we would say that those voters are unrepresented, or that their votes get lost, in the sense that they're not kind of being directly assigned to a representative in this parliament. Our next rule is single transferable vote, or STV, and this works exactly the way that you all think that it would. We eliminate parties with the fewest votes successively until all parties receive at least tau votes. Okay, so how would this work on the same example? Well, the party with the fewest first place votes is C. So C would be eliminated. And we see that the voters who support C have B as a second choice. So those votes transfer to B. After the vote transfer, A is the party left with the fewest votes. They still haven't reached the threshold, so we eliminate them. And we can see that the supporters of A actually have B as a second choice as well. So those votes transfer to B. And we're left with a feasible parliament B and D, where the seats will be allocated in proportion to the new heights of these bars that you see on the screen. Okay, and finally, we have a rule that we call greedy plurality. And here we're going to consider parties in decreasing order of their plurality score and simply add them to the outcome if it's feasible to do so. Otherwise, skip and consider the next highest score. So on the same example, we start with D. The parliament that consists of only D is feasible, so we add that to the parliament. Then we consider A as the next highest plurality score. If we have a parliament consisting of just D and A actually attracts the support of the C supporters, right? They also vote for A on their ballot. So a DA parliament is feasible. Both parties would have support above the threshold. We then go ahead and consider DAB, since B is the next highest plurality score. If we had that parliament, actually B would attract the support of the C supporters, and A would no longer reach the threshold. Therefore, DAB is not a feasible parliament. A doesn't have enough support, so we can't do DAB, and we're left with DA. All right. Okay. Right. So those are the 3 rules we're considering. What I want to do now is tell you a bit about our results. So I'll first focus on some axiomatic analysis to give you a flavor for what sort of properties we consider and the properties that the rules satisfy. And then I'll tell you a little bit about the results from the experiment that we ran. So first axiom to tell you about is called representation of solid coalitions. It's inspired by and very similar to Dummett's proportionality for solid coalitions property. It says that if at least tau voters rank a set of parties at the top of their rankings, then at least one party in that set should be selected. So here's our example from before. We had 5 voters, tau is equal to 5 in this example, who rank B and C at the top of their rankings. I've highlighted B and that group of B and C voters in blue. And therefore, one of B and C should be elected according to this property. What we show is that STV satisfies this property, DO and GP do not. This is probably not surprising to many of you. STV tends to do well in terms of properties like this. One thing to note is that DO and GP, so all our rules, do satisfy this property if we restrict the size of T to equal to 1. So in that case, all this says is that if at least tau voters rank a single party at the top of the ranking, then that party should be selected, right? If you get at least tau first place votes, you should be selected. We call that property inclusion of direct winners. Okay, we could think about varying the threshold. So one natural property that you might want is threshold monotonicity, which says that if a party is selected for a threshold tau, then it's also selected for all lower thresholds. Lowering the threshold should make it easier, not harder, to be selected. And we can show that DO and STV satisfy this property, GP does not. We can actually strengthen this property to one that we call independence of definitely losing parties. This says that, if you increase the threshold, not only should losing parties stay losing, but actually the rule should behave as if none of the losing parties had ever been available in the first place. So it's a strengthening of threshold monotonicity, and it's actually strong enough that in conjunction with the inclusion of direct winners on the previous slide, the weaker of the two properties on the previous slide, this property characterizes STV. Okay. The next property is a reinforcement property. So if a party is selected for a profile P1 with a certain threshold tau1, and for profile P2 with threshold tau2, then it should also be selected for the profile that combines the two profiles and adds the thresholds. So it's a fairly standard kind of reinforcement or consistency property. And actually here we get another characterization result, again, along with inclusion of direct winners. This property characterizes our direct winners only rule. Okay, the last kind of set of axiomatic properties I want to discuss are some to do with incentives, and then I'll get on to the experiment. So we consider a couple of different incentive or strategy proofness properties in this work. The first we call representative strategy proofness, which says that voters should not be able to cause a party to be selected that they prefer to all the currently selected parties. Right? So you shouldn't be able to cause a new party to enter parliament that you prefer to all existing parties. A stronger notion we call share strategy proofness, which says that not only should voters not be able to introduce a more preferred party to parliament, but they also shouldn't be able to increase the seats of their currently most preferred selected party. Share strategy proofness being strictly stronger than representative strategy proofness, yeah. By the observation from earlier that we're generalizing single winner voting, there's really no hope for full strategy proofness in either of these cases, right? Because Gibbard said it the way it applies. So at least in their full kind of generality, we wouldn't expect to be able to satisfy these properties. Instead, what we're going to do is look for kind of politically plausible situations where we might be able to obtain some guarantees, and so that we can still make some meaningful comparisons between our rules in terms of their incentive properties. So to do that, we kind of partition the parties into these categories: safe, risky, and out. So we say that a safe party is one that is selected no matter how I votes. We can think of these as parties that are kind of known to be polling well above the threshold. They're surely going to be elected. Risky, if the party might or might not be selected, depending on how I votes. These are parties that are kind of polling around the threshold. There's some uncertainty whether they're going to make the threshold or not. And out, if the party is not selected, no matter how I votes. These are the small parties. You don't expect these parties to be elected. And what we show is that greedy plurality satisfies representative strategy proofness when there is at most one risky party from the perspective of each voter. So that sounds like a fairly strong assumption, and I guess it is. However, it's also not totally implausible. And when you look at these elections, in practice, there are typically only a small number of parties that are close to the threshold, and in many cases, there really is only 0 or 1 party that is for which there's any real uncertainty about whether it will be elected or not. Just quickly for our stronger notion of share strategy proofness, we can show that direct winners only is the only one of our 3 rules that satisfies share strategy proofness when every voter has a safe party as one of their two most preferred parties. So an interpretation for this is that, sure, we allow voters to have a smaller party as their most preferred party. Maybe these small parties represent niche interest groups, but as either a first or second choice, every voter has a bigger party. So maybe these bigger parties are, kind of representing wider ranges of interest and capture at least everyone's second choice. We also show that under a restriction where voters can only misreport by taking the parliament in the truthful profile and promoting their most preferred selected party into first place. So under that restriction, DO and GP satisfy share strategy proofness, whereas STV does not. Okay, I know I threw quite a few results and properties at you there. Here's a quick summary. Not all of these properties have been ones I've discussed right now, but this is the full set of properties we consider in the paper. Roughly speaking, the properties towards the bottom here are strategy proofness type properties, and the ones towards the top are representation and efficiency type properties. So we see STV has all these crosses at the bottom. It doesn't do so well in terms of strategy proofness and monotonicity. Does do well in terms of representation and clone proofness. DO and GP are kind of the opposite. They do relatively well in terms of our strategy proofness properties, but less well than STV in terms of representation. All right, now with the couple of minutes I have left, let me tell you a little bit about this experiment that we ran. So we conducted an experiment during the 2024, so last year's election of the French representatives to the EU Parliament. Essentially what we did is we put the survey online. We kind of introduced the problem, explained the threshold, explained some of the potential issues, and then essentially asked people to vote, assuming that they could vote for more than one party. So we gave them the choice of, we asked them to first give us a second choice and then give us a ranking of as many parties as they wanted. And the idea is here simply to compare how people vote and how the rules perform when we allow them these additional choices. We had two participant groups. We had a little over 3,000 people who opted in from social media recruitment. These people were unpaid. They tended to be left-wing, young, educated, the sort of people you might expect to complete the survey for free on their own time. We also had a more representative sample that we recruited through a polling institute. We paid them a fixed amount to participate. So we had 1,000 participants who are representative of the French population along various dimensions, various demographic dimensions, and I forget, but possibly also along some kind of crude political dimension as well. Okay, so what do we see? The first thing that we wanted to consider is to look at lost votes. So in this self-selected sample, well, first of all, in the actual election last year in France, we had 12% of votes that were lost or wasted, cast for parties that didn't reach the threshold. It's actually a relatively low number because a couple of borderline parties actually did end up exceeding the threshold. It easily could have been higher. When we asked voters for rankings and then ran our rules, this share of unrepresented voters drops to more like 2 to 3%. So a very big decrease in wasted votes. In the representative sample, this decrease is still fairly significant, but it's less. One reason for this is that in our representative sample, many people simply didn't give a second choice. So we're not able to have their vote transferred to a second choice party. Another takeaway from this is that limited ranking length was actually enough to increase representation. We weren't relying on kind of dropping down to people's 4th, 5th, 6th preferences. So we see here that simply truncating the votes somewhere between the length 2 and 3 is enough to reduce the number of lost votes below what's observed in the actual election. And this, of course, isn't even a fair comparison for our rules because we're not telling the voters that we're going to be truncating their vote. We just took the rankings that they gave us, truncated them, ran the rules, and examined how many votes were lost. So it seems reasonable that in practice, maybe asking people to vote for only 2 or 3, to give a ranking of length 2 or 3 might be sufficient to reduce the number of lost votes. You might wonder if this increased representativeness comes at the cost of increased fragmentation in the parliament, more parties being selected. This isn't really the case. The actual election, France sent 7 different party lists to the EU Parliament. Depending on the sample and the rule, we send between 6 and 8. So it's roughly similar in terms of the fragmentation. Of course, while the number of parties and the set of parties is similar, the seat distribution might be quite different because we're doing this vote transfer. And of course, that's where our additional representation is coming from. There are lots more cool results in the paper. So you can check it out, but in your interest of time, that's all I have for today. So just to wrap up, we've studied these rules for electing parliaments with thresholds. The main message is that you can increase representation by allowing voters to rank parties. This will, of course, come as no surprise to most people listening to this talk. That seems kind of obvious. But the goal of this work is to formalize that and provide some more evidence to hopefully push people who are thinking about implementing these things in the direction of moving to rankings and some ranking-based rules. So I'll stop there and happy to take any questions.
Right, let's thank the speaker. And there have been a number of questions, though your co-authors have been answering
Good.
a lot of them.
That's what
So
I'm glad to hear.
Yeah, I'll first leave the floor open to anybody who has asked questions, if they have any kind of follow-up that they directly want to ask Rupert. Bill, do you have
Yes,
any?
I had suggested something that was very close to what you did in the actual experiment, which was to limit the choice to 2 parties. But I was thinking of telling them that their choice is limited to 2, because that might have a salutary effect in terms of stability and backing of parties that can actually win in a representative. It affects the strategic nature of the vote, I would think.
When you say telling them that they're limited to 2 choices, you mean telling them that they're, I mean, we did in the first part of the experiment tell them that they only had 2, tell them that they could go as a first and a second. So they did, the results I presented here were actually all based on the full ranking versions. But we did also, we ran 2 versions. First, we said, you vote if you could give only a first and a second choice. And then we said, okay, forget that. How would you vote if you could give us a full ranking? And in the paper, we have some analysis for both. Theo can maybe speak better to that. I think that the results are not kind of drastically different between the 2 versions.
As
Does
a
that answer the question?
But as Bill said, if they have 2 choices, people are more likely to put a big party in second, and when they can put a ranking, well, they will put the big party later on in the ranking.
This might affect the actual seat shares of the larger parties in the final election, conceivably.
Right, yes.
I have a question I just posted. So was there any difference in, maybe you already mentioned this and I kind of missed it, but was there any difference in the voting behavior when you were using the different rules? Because if I got it correctly, you were telling them which rule you'll be using and then allowing them to vote accordingly, right? And or did you collect the votes and then just apply different rules on the votes?
So, right, the latter. So we were
okay.
we were vague, deliberately vague about exactly how the rules would be implemented.
Mm-hmm.
I think because we didn't, you know, it wasn't clear that it's not clear that people are going to understand the nuance or really pay attention to the nuances here when they fill this out. So we told them something like, did I have a my PowerPoint skills are lacking.
Yeah, I suppose it's hard to do this because like
But
people take time to really internalize the system. So like once the system has been placed for like a year and people discuss with their neighbors and whatnot, and then they you know, the strategic concerns start to come out. So it's hard to do this over a survey. I agree.
So we you can see here, this is an English translation of
Mhm.
of what we told them for the version where they get to give a first and second choice. But we say if the first choice receives at least 5%, your vote is counted for the first choice. First choice receives less than 5, your vote is counted for the second choice. If the second choice still receives less than 5, the vote is ignored. So it has this kind of vote
The
transfer
constraint
feel,
part.
but it's not a well-defined rule.
Yeah.
And
Yeah.
I mean, I think I would conjecture that voters would behave similarly if we had presented a more precise definition of one of our rules, but you know, you could disagree. Peter?
Yes, for clarification reasons, right at the beginning, you were talking about voters being represented.
Mhm.
And then you told us that every voter basically is represented by their top candidate. But in order for your entire presentation to make sense, it's necessary that if a voter puts a second or third party on the ballot, and if that party gets a mandate, this voter is also counted as being represented. So what is the precise definition of a voter being represented in an outcome, distribution of mandates under your systems?
Right, that's a good question, and I appreciate I was a little vague. We say that a voter is represented if one of the selected parties appeared on that voter's ballot. In other words, that voter's ballot is kind of directly contributing to the vote share of some party in parliament. We say, and so kind of the flip side of that is that we say a voter is unrepresented if no party that appears on their ballot is elected to parliament, which is maybe a funny use of representation. I guess it's the equivalent to saying a voter is unrepresented and to say that their vote is lost or wasted, which is how kind of it's phrased in the discourse around these things.
So then it's my impression that if you take single transferable vote, it's clear that every voter, for every party which he has on the ballot, he may influence that party actually as being elected. But this other system, I think the first one you mentioned, doesn't seem to have this guarantee.
If every voter casts a full ranking, ranks every party, then they will by definition be represented. Their vote will not be lost. So it's to a large extent a function of how many parties a voter ranks, which is why we're also interested in the idea of how much, you know, so if we can kind of trivially say as long as everyone ranks all the parties, then there'll be no unrepresented voters. It's not a very valuable thing to say. So we're also interested in saying if we truncate the votes and only allow people to vote for 2 or 3 parties, will we in practice see that you know, one of the top 2 or 3 choices of most voters will be selected? And that is what we see.
Okay, now I was referring to something else. Is there a guarantee that if you put a voter on a candidate or a party on the ballot, that during the iterative process of determining the outcome, that ballot will be still considered at a stage where this party still may become selected?
For STV, that seems
for STV, it's clear that it is.
For STV, it's clear, right?
Yeah, that's a system I have been studying already 50 years ago.
Right. Right. So for something like direct winners only, where we just choose the parties that are above the threshold,
Yes.
I guess the notion of a stage doesn't really make sense. But in that case, you will be represented if somewhere on your ballot appears a party that received at least tau first place votes.
But your choice doesn't then have any influence on the actually distribution of the mandates. If
No,
you use
it does.
single voter only.
If you're using only So under the rule where you select all parties who receive at least tau first place votes, right? Those parties get selected, but then the distribution of seats does depend on the rankings on the full rankings of the voters, because every party is allocated seats. They're selected based on the number of first place votes, but their distribution depends on given the set of parties that are selected, right? That's now fixed. Now we say for how many voters were we say for how many voters was party A the most preferred party among those selected. So even if you didn't rank one of those parties in first place, you ranked them third, fourth, and fifth, your vote will go to the party that you ranked third.
Okay, that part of the process wasn't
Okay,
clearly
good.
explained. Thanks.
Right.
All right. Let me see. Okay. Are there any other questions?
I would have a question.
Yeah.
And I think this, I mean, the incentive issue, I mean, there was, in terms of the normative properties, the single transferable vote seemed particularly attractive, except for the incentive issues. And so I think in a discussion, and certainly once we think of putting anything into place, especially if you talk into parties, people, and of course there can be the parties themselves will in their campaign behavior and so on, will try to exploit incentive issues. So it will be important to explore in a way how serious they are and how realistic they are. So have you thought in any way to set up, I mean, it would be natural to set up maybe artificial experiments where one uses some constructed situations where theory would suggest, okay, that's where manipulation is attractive. And then, okay, even in terms of different framings, elicit more or less of the suspected behavior, and maybe compared with other rules or so, something like that.
Right. Yes, I agree. And now I'm kind of shooting from the hip beyond what we explicitly write in the paper. But in practice, this idea that parties that voters are so nervous about voting for a risky party seems to me to dominate the strategic landscape, at least in real elections. And I'd be interested in to what extent these, like, it seems like any ranking-based rule will avoid that problem.
You mean nervous about risky, that to make sure if their most preferred is kind of marginal, they would definitely vote for that?
Yeah, risky, maybe risky is the right, risky, maybe the risky. Well, if their most preferred is likely to not get in, then people will avoid voting for that party.
Yeah, but isn't that one of the key issues of kind of for the marginal? That would be exactly, well, I have to preserve now this party, or I want to make sure that's actually a big contribution I can make. And that's an obvious trade-off. And it's not even clear how, when you say the difference between a single voter and a small coalition of voters, it's also hard to model, I think.
Right. Yes, I agree. So I agree it would be interesting to examine the extent to which these incentive issues kind of are prominent depending on the rules that you use. And we haven't really done that. There is some analysis in the paper around strategic voting, but it's not, we never actually ask people. We don't have a way to tell people's true preferences in our setup, so we can't make any strong conclusions.
If I could chime in briefly. So yes, axiomatically, STV doesn't look that great here, but my intuition about STV is that the way it's manipulable is kind of random, like it's NP hard, and it's kind of weird edge cases where it is. And so it's not obviously exploitable by a party giving one piece of advice. So from that perspective, I don't think we can say anything about STV compared to the other rules.
I have a quick question. So the the wasted votes, actually going back to what Peter was kind of saying, the wasted votes is a little bit of an extreme measure because, for example, if you imagine fully ranked elections where everybody submits a full ranking, then there is no wasted vote. But it's a little bit silly because somebody might only be represented by being represented by the least preferred party, right? I mean, one can imagine like any number of like kind of more nuanced measures of representation where, for example, you can do harmonic scores where you are represented at level 1 if it's your top party, half, 1/3, and whatnot. But do you have like based on your kind of experience working on this project, do you have a preferred way of thinking about representation that extends nicely to fully ranked elections?
We have plots. So not exactly these, but these plots get at the idea of how many voters were represented by their first choice, their second choice,
Right.
their third choice, and we don't go beyond simply giving those plots in the paper. But you could do, you could take those and do with them what you wanted in terms of some kind of score.
But once you kind of like change the definition of how much you are represented, now it could also affect the constraint itself, because now you might say that there is kind of this representation measure, which is basically how much representation a party is bringing, which now might reduce if the party is only representing some voter at like a half level because of being their second choice, right? And then now this nuanced measure of representation needs to be at least tau. So it can kind of change the whole setup, I suppose, if you do it that way.
Right, and I at least haven't thought about I haven't thought about that in terms of defining rules or changing the model.
On the other hand, it kind of seems like dropping the representation level also seems weird, because like if you prefer this like very little party that like perfectly aligns with your view, and then like this major party that is like maybe almost aligns with your view, right? There's no reason why you should drop to like half the level by putting the, I mean, then I would like actually start to manipulate and like put the major party first so that this party gets more representation from me. So it's tricky to do this. All right. Are there any other questions? You won't get to ask any other questions to a COMSOC seminar speaker for another 2 months if you miss your chance now. 3 months. All right. In that case, that concludes today's seminar and this academic year's iteration of the series. And we hope to see you all back here in September. And we'll announce the date, time, and everything well in advance. But it would be as usual towards the end of the month. So, all right. Thanks all for joining.
Bye-bye, people. Have a nice
Have a great
summer.
summer.